Welcome back to Office Hours with Dr. Clark. So I wanted to spend some more time on position of equilibrium and curved arrows. Okay, so last time we looked at a couple acid-base reactions and we did position of equilibrium problem. Let's look at an example. I sometimes forget my pKa's. But I'm going to pull up a pKa. pKa is here. Let's see. Okay. So I'm going to see, here we have acetic acid plus, I'm going to look at H. Oh, let's look at water, acetic acid. And then the thought is we're going to lose the proton in acetic acid. We're going to form hydronium. So we're going to see, is this a favorable reaction? So I need the pKa of hydronium, and that pKa is negative 1.7. The pKa for acetic acid, pKa 4.75. So now the question is, what direction is my equilibrium gonna dominate? Is it gonna be going towards my products, which is acetates and hydronium, or is it gonna go? Is gonna favor reactants, which is water and acetic acid. So remember what I said in the last video, the reactions, these acid-base reactions always go in the direction of the weaker acid. So the weaker acid is which? Exactly. The acetic acid, it has the higher pKa. Right? So that's actually a negative 1.7. Um, this is 4.75, just to be clear. Um, so my equilibrium is going to favor that direction and less that direction. So that's why acetic acid is a weak acid. Because when it reacts with water, which is how we measure pKa, it doesn't favor a lot of hydronium formation. Actually, more favors, keeping the acid intact versus losing its hydrogen. So that's how we can determine what direction my equilibrium is going to favor. And we can do our curved arrows. See how I'm doing that? So I'm pulling the hydrogen off because this is a base, right? So we can label these acid, base, conjugate, base, conjugate, acid. So let's go with some terminology here. So we have our acid. So the base part of the acid is called the conjugate base. So you see the pairs. So those are paired. And then the base and the conjugate acid are pairs, right? So the acid loses a proton, becomes a conjugate base, and the base gains a proton, becomes a conjugate acid. So the arrow always starts from the base and it lands on the hydrogen, and then the bond between the hydrogen and whatever atom is connected to is broken, and then the pair of electrons become a lone pair on that atom. Okay? Just for clarity. So that's how we can look at position of equilibrium. So let's look at some other reactions, and then we're going to talk about how can we identify acidic protons. So let's see. Here we have, this is benzoic acid, very popular food preservative. And we have methoxide. There's a negative charge on here. So I'm just gonna draw the arrow right here. And then the products that we're expecting is benzoate and methanol. Now, after doing organic chemistry for many years, I know that this reaction is very favorable because I've, done similar reactions. But let's prove why it's such a favorable reaction, why I drew the arrow going to the left, immediately. pKa is around 16. pKa is, it's like it's 4.2. So this is clearly going to go in the direction of the methanol, because that's the weaker acid. In other words, a more stable acid. So chemistry always goes downhill. It goes from unstable reactive species to more stable, less reactive species. So your benzoate is a way more stable base than methoxide, because this one can have resonance stabilization. This one does not have it. So, and then your benzoic acid, therefore, is a stronger acid because the conjugate base, remember, let's label acid, conjugate base, conjugate acid. So remember, if I'm looking at using Ario, I'm comparing these two acidic species, my methanol, my benzoic acid. They both have a negative charge on an oxygen, so I can't use atom. But the benzoic acid has resonance stabilization, and the methoxide does not. You cannot draw a resonance form for this. So that makes this the stronger acid than this, which pK indicates. And then the bases, this base is going to be way stronger than this base, because this base is not resonance stabilized, whereas this one is. So then we can draw our curved arrows to see if you can do it before I do. Using the example above. See what I did here? Yep, you got it. And that's how we do our curved arrow. So now we're showing how bonds are formed. Whereas with resonance, we're just showing how the electrons were reorganizing themselves in the molecule. With these reaction curved arrows, we're breaking single bonds, which we didn't do in resonance. And we're joining two different species. In resonance, we're doing everything in the same species. So this is some more examples of position of equilibrium, as well as curved arrow notation. All right, see you next time.